Now this is lecture 7 in network theory. So in this lecture we are going to discuss about two important laws. Is Kirchhoff laws, KCL, Kirchhoff's current law, and KVL, Kirchhoff's voltage law. So before that, so what we discussed in lecture 6, the other two parameters, that is inductance parameter L and capacitance parameter C, we discussed. That is the magnetic flux is directly proportional to the current flowing through the inductor, and the voltage across inductor is equal to L into di by dt. And if I want to find the current, so I have to integrate with the voltage dt, 1 by L integration of v dt. Now what is the energy stored in inductor? WL is equal to half Li square, that is at an instant of time. So what is the current is there? So half into L into I square, right? Otherwise we can find the power P is equal to V into I, or we can say Li di by dt. Now if I want to find the energy, so I have to integrate the power, right? Now similarly, the charge on the capacitor Q is directly proportional to the voltage applied on the capacitor, that is Q proportional to V, and Q is equal to C into V. Now what is the current flowing through the capacitor is C into dV by dt. And if I want to find the voltage, so I have to integrate the current. So V is equal to 1 by C integration of I dt. Now similarly, we can find the energy across the capacitor, that is half CV square, right? Now in this lecture, we are going to define the KCLs and KVL. Now before that, so some background required, that is what is the lumped parameter network and a distributed parameter network. Now already discussed the lumped parameter and distributed, so elements, right? So that is the small portion of any large transmission line network we can have, like a resistor or inductor wire. So the two or more elements with connecting wires, so generally it is called lumped parameter network or lumped network. That is, so only it cannot be like maybe 10 resistance maximum or like that. So 10 components will be there, so which is a big network, but rarely we will get that, but maximum we'll see 4 or 5 or 6 elements, right? R1, R2, R3, etc. Now if I see the distributed parameter network, so there will be infinite number of small elements, right? So this is one portion of this distributed network. So like this, you will have so many number of small elements like this. So that's why it is called distributed, but this one is like a simple lumped parameter network. Now in network theory, we have only sees the lumped parameter network. So very small or 2 or more elements, that's it, maximum 5, 6, etc. Right? So that is the difference between lumped parameter network and distributed parameter network, right? Next we have to define some simple parameters, or we can say definitions. Now what is a node, path, and closed path or loop or mesh, right? And what is a branch and what is a network, right? If I say the node, so node is at an, suppose one or two or more than two branches or elements are connected, so that is called a node, right? At least two branches should be there and more than two also. So this is a node, right? Now what is a path? So path is a, suppose if I start from this node, right, this node should not repeat, that is from here to, suppose if I move to 2, so this is generally is called a path, right? And from 3 to 1, if this is a one path, and similarly this is a one more path, right? And see, this is one branch, that is from node to node. So generally we say a branch, right? It may be a resistance, so it is a one branch. So it may be a voltage source, right? It's a one branch. Maybe a current source, so it is a one branch, right? Right? Now what is a closed path? So closed path or mesh, generally if I start from this node, so I should be ended with this node only, right? So suppose this is the path around this loop, so we have to end with this, and any node should not repeat, right? That is a closed path, or we can say mesh. Similarly, if I start from here, so I will end again with a here only. So this is a one loop or mesh, right? Now similarly, so I already discussed what is a branch. So branch is between two nodes. If I start here and end here, so between two nodes one element is there, so that is called a branch. Now what is a network? It's a collection of the branches and nodes and loops, right? Now it's very simple. Network is like a simple building, right? Network is like a building, and the rooms will be there. So the rooms like our loops, right? So that is about network, right? So I hope you got what is a node and what is a path and what is a closed path, a loop or mesh, right? What is a branch? Now one more important point we need to know is, suppose if I draw a network, so you will find so many nodes and branches, right? But there should be one common point or reference point. This is R1, suppose this is R2, suppose this is R3. Now always the entire network theory subject, you have to find a node which is, or we can find a reference node always. There is a point. Suppose this is a 1. See, this is node is not required actually. So only two elements are connecting, so which is not required node. But more than two, we can have a node here. So this node you cannot consider as a node because it's a reference node. So it will consider only one node is existing, right? So we can say principal node also. So this is a reference node, so it will not count as a node. So only it contains one node for solving problems, right? And it is containing, see, this is one loop and this is one loop, and we can have another loop also, right? See, from here to here, the outer loop, right? So that we will see when we talk about the KVL. But we have to consider a reference node. So it's generally we can say common point or ground, right? Or at the ground, right? So these are some notations. So always in network theory we will see it's one reference node, that is common point, ground. So generally we say ground, right? Next one is the first law, which is Kirchhoff current law, right? So Kirchhoff current law states that the algebraic sum of all branch currents leaving a node is 0 at all instants of time. So this is the important point, that is all instant of time branch currents leaving a node is always 0, right? So suppose this is a node which is connecting more than two branches. So suppose I1 is coming and I2 is coming and two currents are leaving, that is I3 and I4. Now if I apply KCL here, right? So the algebraic sum of what is the meaning of algebraic means, suppose there is a current direction is change or any manipulation is happening, that will be added also. So that's why the algebraic sum. So the direction is changing, so we will get negative. So suppose here leaving a node at all instant time is 0. So here if we see two currents are entering, so if I make a positive for those, now they're leaving, we have to give a negative direction, right? Or if you are given the positive direction for leaving currents, and we have to give a opposite direction for the entering current. So if I given the entering current as a positive, the leaving current should be negative. Now that means I1 plus I2 will become is equal to I3 plus I4. Suppose at three branches are here, suppose I1 is coming, I2 is coming, and I3 is also coming. So by KCL, so I1 plus I2 plus I3 is equal to 0, right? So that is about this one, right? So depending on the how we are assuming, suppose you are assuming the leaving current positive, so always will be negative, right? So that is in our hand, so we can give whatever the polarity we need. So what is this meaning is, the sum of entering currents is equal to the sum of leaving currents. This is other way of defining the Kirchhoff current law. That is sum of entering currents is equal to sum of leaving currents. Now, so the other way we can go for like this. So what is the current I, which is dq by dt. Now if I replace with the currents, I1 is equal to dq1 by dt plus dq2 by dt is equal to q3 by dt and q4 by dt. Now the important I told they are all instant of time, so the instant of time is same current, so I can say q1 plus q2. So other notation I am giving, q1 plus q2 is equal to q3 plus q4. That means whatever the charges are entering, that must be leave, right? That is already discussed, the conservation of charge, right? At a node, no charge cannot store or no charge cannot be accumulate there, so it will be only transfer. That is, charge which enters a node must leave that node because it cannot be stored there, right? So this is about the Kirchhoff current law, right? Now the next one is Kirchhoff voltage law. Here also Kirchhoff voltage law states that the algebraic sum of all branch voltages, right, around any closed path. So this is also important, that around any closed path or closed loop of a network is zero at all instants of time, right? This is a statement of KVL. Algebraic sum of the all branch voltages around any closed loop of a network is zero at all instants of time. Now we know that what is a voltage. So voltage is nothing but the amount of energy is required to move a unit charge, right? Suppose a unit charge at A, and we have to move from A to B, then B to C, then C to D, and again D to A, right? We are working on from moving from A to B, then and so on, right? So that is, we are working or we are wasting energy to move this one, so that will become a voltage. So now when you are writing a KVL, always we have to give some notations again here. Now this is already given, so go with the direction. Suppose the loop direction is like this, so you are touching the negative sign for the voltage, main voltage, so that's why we are getting minus. Now when you see here, you are touching with the plus, that is plus V1 plus V2 plus V3 and so on, right? So the moment we give the sum notations, we have to follow that notations only, right? Next, so what is the algebraic sum of all voltages is equal to 0. Sometimes, see, if you see here, this is the main voltage, so there will be some drops will be there and some raising will be there. So whenever it is moving from A to B, it is a raising drop, or it is a raising voltage. And when you see here, it is entering into the positive terminal, so it will be drops. So these B to C and C to D and D to A are the drops. The only one is rising is the main voltage V, right? Or we can say this is the voltage to delivering the power or delivering the energy to this network. So this is the raising, and these two are the resistors which are there. Only it will absorb the energy. That means it will dissipate. So that's why we'll get drops here, right? That is the here. So these V1 plus V2 plus V3 is equal to, these are the drops and this is the raising. That is the other way of is the sum of voltage drops is equal to sum of voltage raises, right? The drops are which is dropping, right? So suppose current is flowing, so the voltage drop across R1 is V1. That is a drop, so it is dissipating, right? And in form of energy, we can write like this. That is, this is a conservation of energy. That is, so energy cannot be created nor destroyed, so it only transformed, right? So here it will be transformed into the resistance, so it will dissipate as a heat, right? So this is about the KVL, Kirchhoff voltage law, right? Now so these are the most two basic important laws. So if I take one example, right? Suppose this is like this, plus minus V and R1, R2, R3, 3, right? Now, so when the circuit is given, always you have to first to draw the one node which is reference node, that is common point. Now how many branches are there? See, from here to here one branch, from here to here one branch, from here to here one branch, from here to, so this is the short circuit, so here to here one branch. So the branches are 1, 2, 3, 4. So branches are 4. What are the nodes? So nodes, we can say 2 or more than 2. So generally it will not be considered as a node, but the exam point of view they will consider as a node, right? So this is 3 branches are connecting, so we can say this is 1, 2 branches, so at least 2. So 1, 2, 3, right? So here, so we cannot say this is a branch. If there is a resistor here, then we can say branch or the node. So here nodes will be 3. Now how many loops will be there, or closed path? So if I start here, so if I go like this, I will get one loop. Similarly, if I go like this, I will get one loop. And if I go the outer loop like this, I will get loop. So the closed loops are generally loops, we will get 3. But to solve the network, so how many loops we need to use, that is another concept, right? So this is how to draw like this. Now if I want to draw, or if I want to apply KVL and KCL, so I will give one more example. Suppose this is plus V, this is R1, and this is plus minus V2, this is R2, and there is a minus plus V1 is grounded. Now when I apply KCL or KVL, so I have to give some current here. So suppose this is I1 here, right? And suppose this is some I2 here, and this is some I3 here, right? Now how to apply KVL? Now first the notations are here, but what about the notations here? So I already told, whenever the current is entering into the resistor, always give plus minus. Similarly here also plus minus, right? Now if I apply KVL around this loop, what I will get? Always go with the direction. So when it is going like this, it will touching with the negative terminal, so minus V, and again it is touching with the plus, so plus. Suppose this is some so V2 is there, V1 is there, suppose this is V3, so this is simply V3, and if I go with this, so it is touching with the plus V2, so V2 is equal to 0. So how can I write? So V is equal to V2 plus V3, equation 1. Similarly, if I apply a KVL around this loop, right? So again we need to give some notation, that is V4 if I give here. Now go with the direction again. So if I going like this, it is touching with the minus terminal, so it will become minus V2, and if I going here plus, and it is touching, so plus V4, and see it is touching with the again minus, so minus V1 is equal to 0, right? How can I write this one? Is V4 is equal to V1 plus V2. This is second. Now the third path also will be there, so that is like this. So I can write the outer loop, the outer one like this, right? Now if I go like this, so it will touch with the minus V plus V3 plus V4 minus V1 is equal to 0. So if I rearrange, so V plus V1 is equal to V3 plus V4, this is 3. Now whenever you are getting the minus or plus, so we can say sum is drop, one is raising, right? So anyway, that is not matter here. So only algebraic sum of the voltage around any closed loop will become 0, right? So that is our some example about the KVL. So we can also give for one example using KCL. Suppose some circuit is like this, 1 ohm, and there is a 1 ampere current, right? And this is some 2 ampere current, and resistor is there 1 ohm, and this is some capital I, right? And always remember, again we need to give a reference time. Now if I apply KCL at this node, the main node, see the I is incoming, that is here I can take as I, and this for this branch the current is leaving as 2 ampere and this branch is 1 ampere. Now if I apply KCL around this, see when you are applying, I told you you have to give a polarity, that is if you assume the one is incoming for positive and leaving, you should have assumed the negative, right? Now algebraic sum, so entering is a positive but leaving is a negative, so -2 -1 is equal to 0 amp. So what is capital I? It should be 3 amperes, right? So now is it satisfied? Yes, because if I is equal to 3 ampere, then only it will divide like a 2 ampere and 1 ampere here. So this is applying KCL here, right? So in the next lecture we'll see some more on this KCL and KVL, as well as the other topics like parallel voltage sources or parallel current sources, right? So that we'll see in the next lecture. Now we'll see what are the features of KCL and KVL. So KCL applies to any lumped electric circuits, right? So already discussed what is a lumped electric circuit. So few elements will be there in a lumped electric circuit. So KCL applies to any lumped electric circuits, and it does not depend on type of element, right? It is independent of the nature of type element, right? It may be linear, non-linear, active, passive, unilateral, whatever. So we can apply KCL, and the KCL follows the conservation of charge, that is the charge will be transferred from one point to another point, right? It will not store at any node. Now similarly, what are the features of KVL is, so it is applies to again any lumped electric circuits. Again, it does not depend on any type, what is the nature of element, right? So what is the type of element, and it is follows the conservation of energy, right? So that is some features of KCL and KVL. Now we'll see if I connect some sources are in series, some sources are in parallel, what is the equivalent we need to take? There is series and parallel connected sources. Suppose one voltage source is there, V1, and one voltage source again connected in a series, so it is a series voltage sources. Now it can be replaced by, see if I apply KVL here, see suppose this is a voltage V, the equivalent voltage V. Now if I apply KVL like this, so what is this? Minus V2 minus V1 plus V equal to 0, right? I'm giving the direction like this, so I'm entering into the negative, so minus V2 minus V1 plus V, suppose it is entering into plus, so what is V? V is nothing but V1 plus V2. Now this total is represented by the one voltage source plus minus, which is V1 plus V2. So this is one way of doing, right? Now suppose V1 and V2 suppose are in parallel, right? That is like this. Now it can be replaced by simply one voltage source, which is V1 is equal to V2. That means parallelly the voltages should be equal. Similarly, if you apply KVL, how it will become? See, if you apply KVL around this loop, so it is minus V1 plus V2 is equal to 0, right? So around any closed loop, the voltage sum should be 0, that is V1 is equal to V2 should be there, right? That is like this. So plus 1 volt, suppose plus 2 volt is there. So if you apply KVL, so minus 1 plus 2 0, so 1 is equal to 0. Is there any possibility like this? No. So that means here the KVL will be fail, right? The KVL fails, that means the circuit cannot exist like this. So the existence means, suppose this is 2 volt, the other voltage if you draw also it should be 2 volt, then only the KVL satisfies, right? So this is about the parallel connection. Series connection is very simple. Suppose if I take one more example like this, plus minus V1 and here minus plus V2, right? Now if you see, these two are the opposite directions, right? Now to find the equivalent, so that depends, right? So for that, suppose if I assume like this, so apply KVL again here, what you will get, now it is touching the positive terminal, so plus V2, it is here touching the minus, so minus V1 plus V equal to 0. Now what we need, is V, so minus V1 is going that side, so it will become plus, and plus V2 is going that minus V2. That means it will be equivalent by one voltage source, which is V1 minus V2, right? So series, so it will be add, or depending on the polarity, it may be subtract also, right? So this is the series and the parallel connection of the voltage sources. Next we will see the current sources, series and parallel, right? Now it is like this. Suppose one current source is like this, I1, and one more current source is coming, I2, right? So how can we equal, or any equivalent circuit can be? If you apply KVL, KCL at this node, so I2 is incoming. So for incoming, if I assume positive, and at this node A, the I1 is leaving. So for leaving, I have to assume the opposite direction of the incoming. So I1 minus I2 equal to 0. That means I2 minus I1 equal to 0. So I1 is equal to I2. That means we have to replace one current source, which is I1 is equal to I2, right? That means if this is 1 ampere, this also should be 1 ampere. Otherwise, the KCL fails. So that will be violation of KCL. So that type of circuit cannot exist. That is like this. So this is 1 ampere and this is 2 ampere. This is not possible at all, because here at this node, if you take here, KCL fails, right? Violation of KCL, so it doesn't exist. Only it is a correct way. This is 1 ampere means the 1 ampere should come here also, right? In series, the current is same. That is the final conclusion. So in parallel, voltages are same, and opposite, or we can say dual, is the current in series will be same, right? So it can be replaced by simply 1 ampere current source, right? Similarly, if I take a parallel, that is like this. Suppose this is I1 and current I2 is here, right? Now how can I replace with this? Very simple. Now both current directions are upward, so the current direction is also upward, and it will become I1 plus I2, right? Now you can apply, suppose this is a node here, so if you apply KCL here, so what is this? I1 is coming and I2 is coming, so it will be added to I1 plus I2, right? Here I1 is leaving, here I2 is leaving, so what should be this current? I1 plus I2. So it can be replaced by like this, right? Suppose if it is like this, I1 is here and I2 is here, right? Now what is the equivalent you will get? So apply KCL, you will get, suppose this is the current I is leaving, right? So at this node, I1 is coming and I2 is coming. So apply KVL. If you assume incoming current are positive, so I1 is positive, but these two are leaving. So minus I minus I2 is equal to 0, right? So what is I here? I is equal to I1 minus I2, right? Now current direction is, suppose if this is the main, suppose if I1 is larger than I2, then only the current direction will be upward, which is I1 minus I2. Suppose I1 is equal to 2 ampere and I2 is equal to 1 ampere, then this will be upward, and the resultant current is 1 ampere. In the second case, suppose I1 is equal to 2 ampere but I2 is equal to 3 ampere. So what is I1 minus I2? We will get minus 1 ampere. That means the current is, whatever we assume that is upward, it is minus 1 ampere. So minus 1 means the opposite direction will come. That is, it should be in the downward direction, which is 1 ampere, right? So whichever the current is high, the equivalent current direction will be like that only. If I1 current is higher than the I2, then it will be upward. If I2 is greater than I1, the current direction will be in downward. That is about the current sources in series and in parallel, right? Next we will see the series resistances, right, and parallel resistances, right? Now, so series resistances, right? Suppose a network is like this, plus minus V, and two resistance are in suppose series R1, R2. Always this should be grounded. Now if I assume some current I here, right? Now again, how to apply KVL, whatever. So when you are giving a direction, so this is incoming, so plus minus here will be there, and here also plus minus. This one, suppose if I assume V1 and this is V2, right? If I apply KVL around this loop, single loop, so entering, that is minus V plus V1 plus V2 is equal to 0, right? But what is V here? V1 plus V2, equation 1, right? If I want to find the equivalent resistance across this loop, suppose if I want to see here, so what is that equivalent resistance? So if I apply Ohm's law across this resistance R1, so V1 is equal to capital I into R1, because in series the current is same, so I into R1 plus across R2 I into R2. Now what is I? R1 plus R2, I is common, so V. So what is V by I? Is nothing but R equivalent, which is R1 plus R2, right? So series resistances will be added. Suppose there is R1, R2 and so on, Rn are in series. So what is the R equivalent? It will be added like this, R1 plus R2 plus and so on, Rn. This is for generalized expression. Similarly, if there is a parallel resistances, so what are the equivalent resistance we need to find? So suppose it is like this, R1, R2, right? And this is some voltage V, and this is current I, right? Now how to find the equivalent? Here, see, this is the branch of V, and which is parallel to these two resistances. So can I make like this? Parallelly the voltages will be same, so this is also same, right? Now this branch, if I assume some current I1 here and this is some current I2, right? By KCL, what is this? What is the KCL around this node is? Suppose incoming is I and out leaving currents are negative, so minus I1 minus I2 is equal to 0. Now what is I1 plus I2? Now if I apply Ohm's law across these two resistances again to find I1, so I can take V by R. So the voltage is same, so V by R1 plus V by R2. Now what is V? If I take LCM R1 R2 and this is R1 plus R2 and this is I. Now what is V by I? V by I is, so V is here, so I is coming in this side and R1 R2 is going that side, so R1 R2 by R1 plus R2 is the equivalent resistance, R equivalent. Whenever there is a two resistance in parallel, so it will be R1 R2 by R1 plus R2. So the notation we can write as R equivalent is equal to R1 parallel R2, right? Now, so suppose there are three resistances in parallel, so how can we write? So if these three resistance are in parallel like this, R1, R2, R3, and there is a voltage source V and I. So I cannot write R equivalent is equal to R1, R2, R3 by R1 plus R2 plus R3. So this is a wrong, right? So we cannot proceed like this. Now how to find? Now if you see this expression, this is I is equal to V by R1 plus V by R2. Suppose 3 resistance are in parallel. So how can I write V by R3? 4 resistance are in parallel. We can write V by R4. If I take V common, this will become I by V, which is 1 by R1 plus 1 by R2 plus 1 by R3. Now what is I by V? If V by I is R equivalent, what is I by V? 1 by R equivalent, which is 1 by R1 plus 1 by R2 plus 1 by R3. Now this is a very simple way we can find. If n number of resistance are in parallel, so it will be 1 by R1 plus 1 by R2 plus and so on 1 by Rn. This is 1 by R equivalent. Alright. This is very simple to find the so many number of resistance in parallel. So 1 by R equivalent is nothing but 1 by R1 plus 1 by R2 and so on. So if you know R1, R2, R3 value, so we can find 1 by that value, then we can make the once we get 1 by R equivalent, so we can get the reverse, that is we can make 1 by value of this one, so we can get the R equivalent directly, right? So this is how to do parallel resistances. The last point we need to study in this lecture is voltage division and current division. So voltage division across resistances, similarly current division. This is a very important topic also, right? Now voltage division will happen when the resistances are in series. Resistances should be in series. Now current division will happen when the resistances in parallel. Resistances should be in parallel. So that how to find the voltage division and current division we'll see. Suppose there is a main source V and two resistance are in series, R1 and R2. This is grounded, this is capital I. So this is resistance across V1 and this is voltage across V1 and voltage across V2. Now suppose if I want to find V2 and there is a main source voltage V, how can I find the voltage division principle? Same, if I apply KVL, so it will become V is equal to V1 plus V2. Very simple one. So once you familiar with the KVL and KCL, so by looking the circuit also we can write the KVL equation directly. So whichever is entering into minus and the remaining should be in the opposite direction. So it will be V1 plus V2. Now if I want to find V1 and V2, what is the notations we need to use, right? So we know that R equivalent, so R1 plus R2, right? So that we will see. If I apply KVL and so we got this expression and Ohm's law across this R1. So what is V1? You will get I into R1 and here you will get I into R2, that is V, right? So but I need V1, right? So V1 is equal to, so anyway V by I is equal to R1 plus R2, right? So this is one, right? But what is V1? So V1 is equal to I into R1 by Ohm's law across the resistance R. But if you replace this I from this expression, what is I? I is equal to V by R1 plus R2 into R1, that is V1. So this is how to write the V1 is equal to voltage across the resistance R1 is equal to main voltage into that resistance by the total resistance R1 plus R2. This is a voltage division rule, right? So V1 is equal to V into R1 by R1 plus R2. That is, the voltage across this resistance is equal to main voltage into the resistance across this one by the total resistance R1 plus R2. Similarly, if I want to find V2 across this resistance, it's very simple. Main voltage into that resistance by total resistance R1 plus R2. Right? According to KVL and according to Ohm's law, we will get the voltage division principle like this. Now we will see the current division. So current division will happen when the resistances are in parallel, right? So if I take a circuit like this, so the current is coming I and there is two branches are there, R1, R2, right? Suppose in this branch there is a current I1 and this branch there is current I2. Now how to find this I1 and I2? By current division rule. Suppose if I assume the voltage V across this parallelly, so at this branch what is the voltage V? So same will be across these two, because parallelly all voltages will be same. Now we know that we already found what is the parallel resistance equivalent, that is I is equal to I1 plus I2 by KCL, and I is equal to V by R1 plus V by R2 by Ohm's law, right? If I take V common, it will become R1 R2 into R1 plus R2. This is I, right? Or we can say V is equal to R1 R2 by R1 plus R2 into I. That is equation 1, right? Now by Ohm's law we know that, so across this resistance, so V is equal to I into R1, right? Or I1 into R1, right? So that is like this, V is equal to I1 into R1. But what is V? We already found V is equal to R1 R2 by R1 plus R2 from the equation 1 is equal to I1 into R1. This is R1 R2 into R1 plus R2 I. Now here R1 will be cancelled, R1 will be cancelled. What is I1? I1 is equal to the main current source into R2 by R1 plus R2. So this is one important conclusion, that is, if I want this current across this resistance, the main current source into the opposite resistance of this branch. So we are finding at this branch, that is R1, but we got R2, that is opposite resistance by, again we will get total resistance R1 plus R2. Similarly, if I write for I2, that is main current into across R2 means we have to take the opposite resistance, which is R1 by R1 plus R2. Now this is the current division principle, right? Now what happens when three parallel resistance are there, right? So that also will be there, R1, R2, suppose R3 is here, right? And this is current I, and this is I1, I2 and I3. This is this. Now we know that, again same, this is V, so this is capital I is equal to V by R1 by R1 plus 1 by R2 plus 1 by R3, right? Now if I want to find only I1, so I1 is equal to V by R1, right? If I substitute V here, that is 1 by R1 into main resistance I, that is I1 is equal to I into, so V is 1 by R1 plus 1 by R2 plus 1 by R3, right? Or we can say, it's very simple, I1 is equal to, so I into R1 R2 R3 by R1 R2 plus R2 R3 plus R1 R3 by R1. If R1 R1 cancel, so the I1 is equal to I into the opposite resistances multiplications, R2 R3 by R1 R2 plus R2 R3 plus R1 R3. Similarly, if I write I2 is equal to I into, if I1 is there, R1 resistance is not there. Similarly, if I2 is there, means we'll get R1 R3 by the same parameter will be here. So R1 R2 plus R2 R3 plus R1 R3, right? Similarly, I can get the last expression, that is I3 is equal to I into R1 R2 by R1 R2 plus R2 R3 plus R1 R3. So this is the, so we cannot find like this, right? Opposite resistance, that is R1 R2 R1 plus R2 whatever. So we cannot follow the same principle as the two resistances. We have to follow like this. Suppose if I take like this, so I am going for some example. Suppose 1 ohm, 3 resistance are in parallel, 1 ohm, and this is 1 ohm, and this is some current 1 ampere. So whenever the resistances are same, and this current will be divided equally, right? So 3 parts are there, so 3 parts, that is 1 by 3, 1 by 3, 1 by 3. We can use that formulas what we discussed here for this one, that is the 3 equivalent resistances, and see that we are getting same or not. Similarly, suppose there is a main current source 2 ampere and there is a 2 resistance are in parallel, 2 ohms and 2 ohms. Now 2 resistance are the same, so 2 ampere means it will be 1 ampere and it will be 1 ampere. Now again you can prove like this, right? So suppose this is I1, so what is I1? I1 is equal to the main current into opposite resistance is again 2 by 2 plus 2, right? So you will get 1. Similarly I2 will get 2 into 2 by 2 plus 2, again we will get 1 ampere, 1 ampere. Similarly you can solve for this one, so 1 by 3 ampere, 1 by 3 ampere, 1 by 3 ampere, right? Similarly voltage division also will be there. Suppose there is a 2 volt and 2 resistance are in series. So suppose this is 1 ohm, this is 2 ohms, right? If I want to find V1 and V2 here, so V1 is equal to the main voltage into this resistance, wherever you are finding that resistance, that is 1 by total resistance, which is 1 plus 2. So 2 by 3 volts across V1 or resistance 1 ohm. Similarly V2, that is main voltage into same resistance, that is 2 by 1 plus 2. This is 4 by 3 volts. Now according to the KVL, what is 2 volt? It should be the voltage drops, that is V1 plus V2. What is V1? 2 by 3. What is V2? 4 by 3. So it will be 6 by 3, which is nothing but 2 volts. So 2 volt is equal to 2 volt, right? So satisfying the KVL. Similarly, suppose 2 resistance are in, suppose this is 1 ohm and this is also 1 ohm, right? So then V1 is equal to V2 is equal to 1 volts, equally divided, right? So this is about the KCL, KVL, and parallelly if the current sources are connected, voltage sources are connected, right? And how to find the R equivalents when it is in series and when it is in parallel, right? In the next lecture I will go for the problems on this KCL, KVL and R equivalent resistances, right?